So in the last class, we were discussing this final problem. Has anyone tried this problem? So I have written the answer here, VGS and VSD's value. If anyone has tried, they can match. Or should I solve this question? I am audible, right? Okay. So any one of you would like to comment on how this question should be solved? Anyone who was following? Okay. So if so, uh, Chandrasekhar, would you like to try? Because you have been responsive in the class. Did you try this question, or do you even remember somewhat whatever we did? So we were going through JFETs, and the formula that we saw for the drain current in JFETs is ID equals to IDSS 1 minus VGS upon VP square, not mod, VP square. Okay, and where IDSS is the maximum current, maximum drain current that flows, right? Because this is the current at where? This is the current at VGS equals to 0. This was the current at VGS equals to 0. This is the maximum drain current that can flow. You can see if you put VGS equals to 0, you will get ID is IDSS, right? So this was the formula. Now in this question, IDSS is given, right? IDSS is given, VP is given, and we have to find the other parameters. So what are the other parameters? We have to find basically VGS, and we have to find VDS, right? Now here you can see that the arrow, if the transistor is outside, that means this is a PJFET, right? This is a PJFET. So basically VSG will be positive and VSD will be positive, right? And current will flow, ID will flow from S to D. Okay, current will flow from S to D. So now how will you solve this problem? You have the formula. You have ID equals to IDSS 1 minus VSG by VP square, right? Now the value of VP is given to be plus 2.5. You should know that here the value of VSG will also be positive, or you can write it as VGS itself and that will be positive. Okay. Now ID, if you say what is ID? They have placed a current source. So if they have placed a current source, that means in that branch the current is defined. So ID is 0.8 milliampere. This ID will flow from here, and this is the same ID that will flow from here, because here there is zero current, right? So ID will be 0.8 milliampere, and I had told you that you need not change the all these units. So suppose this is at milliampere and you have IDSS. You have IDSS which is also in milliamperes. So you need not worry about the units here. Okay. So you can directly write 0.8 and 2.5. Here 1 minus VGS upon VP is 2.5 square. Right. So let me write VGS only here. VGS is square. So now what will you do? You just solve this. 0.8 divided by 2.5 is 0.32. Okay, so I can write here as mod VGS, or I can write VSG, whatever is there. So one mistake is here, it should be VGS is positive, because this will turn off for negative voltages. So VGS is positive. Okay, so if you remember the characteristics, I will show you once more. So this is what VGS will be, 1.085 volts. So let me show you the characteristics so you guys quickly remember. Yes, so for a JFET, the value of VGS is positive and VSD is positive. Okay, and for positive values it is going to turn off the transistor for some value, and it starts from VGS 0. Okay, so these were the characteristics. Okay, so this is how we are getting VGS. So whenever you are writing VGS as positive here. So VGS is 1.085 volts. Okay, now we will find VSD from here. So how will you find VSD? So you see here VGS is given, right? This VGS we just found out 1.085. Now VG is given. VG is 1 volt. So what you will do? You put a KVL. You put a KVL to from here to this loop, not here, because this is unknown. The VSD is unknown. So we cannot put a KVL here, right? Right now we cannot. That is not useful. So we will put a KVL here. What we will do? Putting a KVL, that is -1 plus 1.085 plus Vs is 0. So we will find Vs from here. So this KVL will give us Vs. So let me shift this a bit. Okay. So from here, what is Vs coming? Vs is coming to a 0.085 volts. Right. So now I have this voltage. I now have this voltage. I can find Vd also separately. How? I will put a KVL to this loop. Right. Because I know ID. I know ID value, that is fixed, that is 0.8. So what I will do? Minus Vd plus IDRD, that is our IDRD, minus 9 is 0. Okay. So RD is 4 kilo ohm. The current is in milliampere, so you need not change any of the units. So what is Vd? It is coming to be 4 into 0.8 minus 9. So Vd is negative, which is 3.2 minus 9. Minus 5.8 volt. So what is VSD coming? VSD is coming as, where did it go? Did I do some mistake here? Okay, let me just write it, and then we will see whatever the mistake has been done. So VSD was coming to me. I think that should be positive. So VSD is coming, according to here, it is coming to be 0.085 minus of minus 5.8. So let me just check the answer quickly. What is the answer here? Is any one of you getting the answer? I have done some mistake there, I think. Some silly mistake is there. Oh, I have written the wrong answer. The answer is 5.71. Yeah. So I have written the wrong answer. So VSD is coming to be minus 5.8 volt, plus 5.8 volts. Okay. So here I had written it wrong. It will be 5.8. Okay. So is this clear? Please respond if you are done with this so that I can move forward to the other question. So I think it's been 2 weeks that I had discussed charges in semiconductor as excess carriers I had discussed, right? So I had told you that I will discuss one question that came in EC 2022. It was a complicated question. So I will discuss it now. Okay. One second. The screen just went. So we'll go back to the semiconductor question once. Okay. So this was the question that was asked. Okay, I think my screen again went. One second. Oh, I am sharing the screen, but it is somehow not coming. Okay, so it is now coming. Yeah. So the internet is very slow here, maybe because it is raining. That's why. So it will take a bit of time to load. I think you are able to hear me, right? Okay. So we'll start with the excess carrier question first. So we will solve this question and then we will go to JFET amplifiers. Okay. So JFET amplifiers, I think last question was asked in 2002. After that they have not asked. So they might ask it for 1 mark, but there is low chances. Okay. So first we will see this question because now these kind of questions are becoming very prominent and they are asking a lot of questions from this topic as well. Okay. So the question is p-type semiconductor with zero electric field is under illumination, low level injection. So low level injection means there will be minority carrier flow. Okay. So low level injection means there will be minority carriers. Okay. So as they have written, excess minority carrier density is 0 at x equals to plus minus 2 ln, where ln they have given the value is the diffusion length of the electrons. Now assume the charge of electron is this. The profiles of photo generation rate is also given, okay, and recombination rate. So generation and recombination rate, the profile they have given, and they have asked that what is the magnitude of current density due to photo generated electrons at x equals to plus 2 ln. As you can see, this is a numerical answer type question. Okay, this is a numerical answer type question, and also that means that it won't have any kind of objective options given, right? So this is a very complicated and lengthy question. So whenever you are faced with this kind of question that you are not sure of and it's a numerical answer, you should not attempt it like in first go, because these kind of questions there is a high chance of having calculation mistakes and all. So you have to be very calculative in your gate exam about which question to answer, which question to not answer. So let's start with the question. This is the photo generation rate profile and this is the excess minority career combination profile. Okay. So we will see how these both of these profiles are actually used. So the diffusion current is given by this formula. This we have seen, right? You would have seen this formula QdN dN by dx. Now this delta n by delta x I have written in this form, delta nx by delta x. Okay. So this delta nx by delta x is nothing but the change in the carrier concentration. And dN, you know, that is the diffusion constant which is there, right? Now we have another formula which says ln equals to, that is this diffusion length of the carrier is equals to under root d tau. So dn into tau n, right? Where tau n is the recombination time, recombination lifetime, right? So from here we arrive that this formula can be rewritten as this, which I have put equation number A. Okay. So now what's next? The recombination is given as 10 to the power 20 e to the power minus mod x by ln. Okay. From where did this come? R. From where did this come? This is given in the question. Okay. So if you remember, Chandrasekhar had asked one question in the second class in which we had just multiplied this R with tau and we got the answer. Okay, because there was no dependence on the diffusion length there. There was no x. So they had just asked in some condition. We just multiplied R into tau and we got the answer. But here the R is having a proper profile, a particular profile according to which we have to find the concentration. So you can write the concentration delta n of x as R into tau, which will be given with this formula. Okay, 10 to the power 20 e to the power minus mod x by ln tau n, right? So now after having this, just keep it there. So at x equals to ln, what will happen if you put ln? You will get this, what I am written as equation number 1. Okay, now till here everything is fine. Okay, so what was your goal? Your goal is to find delta n of x by delta x, right? But here you have an equation of delta n of x. You cannot directly differentiate it because this is a discontinuous equation, right? So you cannot directly differentiate it. So we have to arrive at another equation. So from continuity equation, this equation is also there from the book. It's an important equation. Continuity equation, you have dn into delta square del nx by delta x square is 0. This is what continuity equation says. Okay, this is 0 because the generation and recombination rate is 0. It is given. This is the profile for generation, minority carrier recombination and generation that was given, right? So this is for generation and this is for recombination. At both the places you can see that here it is 0. G is 0, R is 0, right? At these places G is 0, R is 0. Okay, and therefore this equation is written like this: from ln to 2ln, basically dn and delta square nx by delta x square will be 0. This kind of equation always have a solution like this: ax plus b equals to delta nx. This is the solution. So now we will find the solution just like we do in mathematics, differential equation. So at x equals to 2ln, we know that this is given as 0. Concentration is 0, right? So now we'll just put the value, we find the value of A. Now at x equals to ln, we have found delta n of ln, right? So we'll putting the value equals to A of ln plus B. This is not natural log, this is ln. So I'll just write it again. This is ln. Okay, this is ln plus B. So 10 to the power 20 e to the power minus 1 tau n equals to, again I have put A's value and we will solve it. From here we get B's value. So we have A's value and B's value now, and we will put it in the final equation, which is Ax plus B, right? And therefore we will arrive at delta nx equals to this. So this is now an equation which can be differentiated. So after that, so this is the main equation, and after that what we will do, we will differentiate it and we arrive at equation B, right? And from here we put the value at the first equation, which was the current density equation, q into ln square by tau n into delta of delta nx by delta x. From here, when we put this value, we arrive stepwise, we will arrive at like this, and we will arrive at such a part of the equation where we can directly put whatever is given in the question and we will get the answer. So now you see that this was a question which was having many steps, right? So this is not a very easy question. You have to think about it, you have to follow the steps to find it. So I am slowly going over it again and you guys just try to see it. I will upload this in due time, or these videos will anyways be uploaded in NPTEL websites. I have these videos which I had solved, so you will be getting to know it. Okay, so I'm just slowly going over it, that the photon generation and recombination rate profiles are given. Okay, you are asked at x equals to plus 2 ln, right? So we are taking g equals to 0 and r equals to 0. Okay, because after plus 2 ln, that is what the profile will be. So that will be the condition that we are going to use. So we started with the diffusion current formula. Okay, then we substituted the value of ln. Then we saw that the recombination rate is formula is given. We put the value of ln to get the so that we can later use it in our condition. Continuity equation is given. Okay, from here we know that this kind of equation have the solution as ax plus b equals to delta nx. Now at x equals to 2 ln, what is going to come? That is there. And then at x equals to ln, what is going to come? That is also there. Okay. Now from here we will finally arrive at values of a and b, and we will have the final equation of delta of nx, right? So after that we will just differentiate it once and we come to this equation which is b, and from equation a and b we will find the answer as 0.59 milliampere per centimeter square. Okay. So just have a look at it and then we will start. We'll then start with JFET. JFET amplifiers will start. Okay. Let me know once you have understood this problem. Then I'll start with the JFET. So we will check the JFET small signal analysis. You can see the figure here. Okay, so we have put a DC biasing, right? We have put a DC biasing for biasing the JFET, and then we are putting the AC signal Vi, small vi. So whatever is in small is the instantaneous signal. Okay, so capital is the the DC signal. So VGS is a DC signal that we have applied to bias the MOSFET. Okay, so that it remains in the saturation region. Okay, where it can behave as an amplifier. So now we can see that the small VGS is given by the capital VGS and the small Vi, right? Which one is DC component, the other is AC component. Now this can be written as VGS plus small VGS, right? So now after this, what we know is that the instantaneous drain current is given by this equation. right? Where because I am saying instantaneous, so this is small id and it depends on small VGS, right? And IDSS will not change. It is the drain current at 0 voltage, so this will not change. This is the instantaneous drain current. Now here I am just going to put the value of small VGS that we saw earlier. I will just put this, and therefore we will arrive at this equation, right? So on expanding this equation, we will come at this. On expanding this equation, we will come at this point right here, and from here you can see that the ID is now given by this term, which is because of the DC voltage, this term which is because of the AC voltage, and there is this third term which is the square of the AC, which is basically nothing but distortion due to non-linear component, right? Non-linearity. Now to minimize this distortion, we have to follow this equation. So this can also be asked, like, to minimize distortion what needs to be done. So this is what needs to be done. Okay. So now the drain current is therefore given as the DC drain current plus the instantaneous current, right? So therefore from here we can say that the ID is basically written like this, right? Now from here, so this is nothing but the AC component that I have written. So the small ID, the AC component that we had got here, this one, this is what I have written. Okay. So now delta ID by delta VGS, we can find the transconductance from here, which is delta ID by delta VGS, and that comes out to be this. Now since GM is a positive quantity, it will be using this. So we will take Vp as mod value, okay, and not inside the bracket. We don't take Vp inside the bracket as mod, we take only it outside, right? And maximum GM is therefore given by 2 IDSS by Vp. Okay. Now there is this DC characteristics that we had seen earlier, and we had seen that I had just drawn it like this. So it is not a straight line, but it is a slightly sloped line, right? So this slope is because of finite R out. Now otherwise there will be 0 output impedance. So this is because of finite R out, and therefore ID is given as IDSS 1 minus VGS by Vp whole square into 1 plus lambda VDS. Now R naught is given by this formula, delta ID by delta VDS to the power inverse, and therefore you will arrive at finally this equation. So this is what is more important. So from here we see the small signal equivalent of JFET. So this is the small signal equivalent. Okay. So ID basically constitute of this components. First is what goes from GM VGS, and the other is due to the voltage drop between the R out, R naught, the small R naught, voltage drop at small R naught. Okay. So this is the small signal equivalent. So continue with the JFET question. So MOSFETs only basics we will first see. Okay. So MOSFET is a metal oxide semiconductor. Okay. So basically there is a metal, there is a oxide, and there is this semiconductor substrate that you are seeing here right now. Okay. So the terminal that is connected to the metal is the gate terminal. Then there is this insulator which is mentioned as oxide, and there is this semiconductor which is the substrate. Okay. So this is also a body terminal. So MOSFET is basically a 4 terminal device. Remember this. It can, the operation can be controlled with the body terminal also. Okay. So MOSFET is a 4 terminal device. The current is controlled by the electric field applied perpendicular to the semiconductor surface and direction of current. Okay. So this is just same as JFET. In JFET also the current is controlled by the electric field which is applied perpendicular to the semiconductor. Now the heart of MOSFET is a capacitor. Okay. So we will first see the MOS capacitors working, and then we will see how that is used to make a transistor. So now if you take a normal cap, so this is a normal parallel plate capacitor, you can see in figure A. This is a normal parallel plate capacitor. So in the normal parallel plate capacitor, if you put the voltage in this way, like it is shown, negative and positive terminals, the charges will distribute in this way, right? There will be minus charges here, the positive charges will come here. and the electric field will be in this direction. This is basic, right? So here also what is happening, here there is one metal here and there is one semiconductor substrate here. So this semiconductor substrate and the metal, they are actually behaving as two parallel plates of the capacitor, and the oxide in between is behaving as the dielectric. Okay, so it is behaving as two parallel plate of the capacitor. So now you can see that in the second one, it has shown the MOS capacitor. So the A is the parallel capacitor, in the B is MOS capacitor. So these are so everything I have taken from Niemann's book. It's well explained there. Okay, Niemann's book is not having very detailed explanations. It is just normal explanation for basic thing. Okay, so now you can see that we have a negative bias. That is, the gate is negative with respect to the substrate. Okay, gate is negative with respect to substrate, and this is the NMOS. We will see why this is a NMOS. So the P type substrate is there. So what will happen now, that when I put negative here, the holes will start getting attracted, and therefore in the third diagram there is a accumulation of holes. So this is also known as accumulation phase of MOS capacitor. So when you give a negative bias with on gate with respect to the substrate, okay, what you see is accumulation of charges, right? So P type is filled with holes. When you have put negative voltage, the electric field will cause all the holes to come towards it, right? So one second. So now what will happen, next we will see something else. So what will happen if I put a positive voltage instead of negative voltage? So when I put a positive voltage, what will happen? The holes will get repelled, right? So when I put it's just like reverse biasing a PN junction diode, right? So what is happening? The charge carriers, the movable charge carriers, which are responsible to carry current, they are all going to move away from this area of the substrate, this junction, and therefore you have a depletion region, which is also known as negative space charge region. Why negative space charge region? Because now since the holes have moved away, these ions are present. The ions are present. So no current will flow. These are immobile ions, right? So these ions have come, and therefore what will happen? This is now not having any current, anything. It is just devoid of any movable charge current. Next, what happened? When you now keep on increasing the voltage of the gate, right? This positive biasing voltage, when you keep on increasing it, what happens is, now whatever electrons, because P type semiconductor, the minority is electron, right? Minority carriers will now come and they will start accumulating, and as the electrons come and start accumulating, there is a flow of current, and therefore you have now achieved something. Okay, what have you achieved? So this was a normal MOS capacitor. So now we will see that how it is now going to behave as a transistor. So what we have achieved, we are able to flow a current by applying a bias, right? So if I have a region from here, if I have a terminal from here in the channel, from here, what will happen? There will be a current flow between these two terminals, and the current flow is due to voltage between these two terminals. So I am applying the voltage in some terminal and I am getting the current in some other terminal, which is the basis of the transistorized action, right? You control the voltage in one terminal and you get the current in some other terminal. Like in BJT, you control the base to emitter voltage, and what you get is the collector current, which finally flows to the output, right? So similarly in MOSFET, you control the gate to source voltage, and what you get is the drain current flowing from drain to source or source to drain. That also we will see. I had asked you this question when we were solving the first question, if you remember in our first class. So that is the drain to source current or source to current, drain current will flow. Okay, so this is the normal behavior of the MOS capacitor. So all these regions are called accumulation region. This region is called depletion. Sorry, so this is accumulation, this is depletion, because there is depletion of charges, and then this is inversion. So for working as a MOSFET, we take it to inversion region. Okay, then only it will start working, then only it will start conducting the current. Okay, so now this is the N type substrate. Okay, there's just the opposite is going to happen. So when we put uh, a positive voltage here, positive gate to substrate voltage. So when we are putting positive gate to substrate voltage, the electrons which are there in the N type are going to come. The electrons are going to come because of the electric field. This is for N type substrate. The earlier one was for P type substrate, right? So now the next will be what? You will now start putting a negative voltage. So when you put a negative gate to source voltage, negative gate to source voltage or gate to substrate voltage, what will happen? There will be a depletion region devoid of any mobile charge carriers. When you keep on increasing this negative voltage, the holes that are present in the N type, the minority carriers, they will get attracted, and thus the channel will form. And now the current will be because of this, right? So this is the basic of MOS capacitor. Okay, so just have a look at it, and you can ask me anything if you want. So we started with a normal MOS, metal oxide semiconductor, right? And we see that the there is this metal layer, then there is this oxide layer, and then there is this semiconductor substrate. Now in a normal parallel place capacitor, there are two plates and there is dielectric in between. This and when you put a voltage to these two parallel plates, they start, so how the capacitor behavior is like that, the charges get distributed. So just like that it will happen here also. There is a p-type substrate. In case this is an n-channel MOSFET, there is a p-type substrate, and then there is this gate, and we are putting a negative gate with respect to substrate, and we saw that if we put negative gate voltage with respect to substrate, we get that the holes which are the majority carriers in p-type, they get attracted. Okay, and after that if we put a positive voltage, then there is a depletion region, right? There is a depletion region, and which is devoid of any mobile charge carriers. And after that when we increase the voltage more, then we start getting electrons in that region, and after the electrons are there, we can now start using that current. So I think in next class we will see how this can behave as a transistor, and we will go from there. We will take theories only. uh, if you want, we can take some DC based MOS questions also if we finish up quickly. Okay, so I think we will continue in the next class from here. If there is any doubt, you can ask me. So if MOS capacitors you want to study in detail, you can go to NPTEL and check. I have already given you EDC and analog NPTEL videos, what you should watch, that I have already told you. And if you have not seen, you can go to YouTube and check that. And so second is this Ali Hajmiri's lectures. Hajmiri's lectures. This also has MOS cap, and these are overall very good lectures. Okay, for clearing your basics, these are overall good lectures. So Ali Hajmiri is having MOS cap, but in very much detail. I don't think that much detail you need for gate. So the next class we can take some question of MOS cap as well. I remember there had been questions on MOS capacitors, numerical question, but again those questions are of that category that you should not normally attempt in gate. Okay, unless you are very sure. So that we will see next class, because I haven't check the questions. I thought we will finish the JFET amplifiers, so I haven't uh, checked that question yet. So we will see that in next class. Okay. So any questions to ask, anything, and how is your preparation going? You can tell me if there is any issue coming in your preparation or anything. We have 5 minutes. If you want, we can quickly discuss it. Anyone want to mention how the preparation is going, what they are targeting, what is the subject they normally like, or what is any other subject that you are having problems in? I might recommend you something from my preparation, whatever I had done. That will be fine. Okay then, so if there is no questions, then we can wrap this up today. Then next class we will take it from here, from MOS capacitors. Okay. Can we have more session? No, Mamta. Actually, this is a part of my PMRF TA-ship, and we have only 1 hour sessions to give per week, and I have to wrap up in this session itself. So that's why I'm targeting that I will finish MOSFETs very well, because that is something normally I have not seen other teachers giving more importance to it, and in recent times MOSFETs are asked like anything, like there are questions of two, 3 questions based on MOSFETs. So we will take it to a good level in MOSFETs, so that is clear for you guys. And basically I am an analog designing area, so MOSFETs is something that I should be able to deal with. So I will deal with that, and after that I will deal with op amps whatever time we have. So whatever sessions we have, in that I will manage in that way only. Okay. So try to
I was saying for Thursday and Friday, like because that day the whole day is empty. That's why.
so you want to change the Saturday session to Thursday or Friday, something like that you are saying?
No, ma'am. No, ma'am. We need some more session. I
So that
wanted
is
like.
what is not possible, because this is kind of like a part of my TA duty, and I also have like other TA responsibilities in IIT Kharagpur as well, my research also. So like taking out this 1 hour is basically very difficult for me. So but yeah, this is a part of my responsibility, so I am doing the TA duty like that. So I am afraid we cannot have more sessions as a part
Okay,
of the
ma'am.
GATE NPTEL thing. So I am afraid we cannot have. So we are limited to some number of sessions that we have to fulfill.
Okay, ma'am.
Okay. Okay, then keep on practicing. Okay. Okay. Bye.